All right, today we will be talking about the ADAPT-VQE, or the Adaptive Variational Quantum Eigensolver. This is a NatCom paper from 2019. It's very popular. It's been cited many, many times. There's many variations of it. It's even popular enough that it's in like Qiskit Nature. So yeah, it's kind of surprising. I guess I see a lot of these style of papers that I'm always kind of confused by, simply because I'm not really into the quantum chemistry world, but the figures that are always in these sort of papers show a lot of these number of parameters versus the basically the error of the energy. But I always thought like the energy error could be like 10 to the -8th or something was good enough in terms of like chemical accuracy. I forget exactly what the chemical accuracy is, but it's very interesting because a lot of these papers present errors like 10 to the -14th. I'm like, that's like the error that exists just in the floating point representation on your computer. So it's just very surprising. I don't know. That's tangential. Just if you look at any of like the variants of these papers, you'll see what I mean. But the ADAPT-VQE itself is a very simple concept. Basically, a lot of the physics or chemistry informed circuit designs are really inefficient from a gate-based side of things. You need lots of 2-qubit gates, lots of depth, so it's going to be a long time before those are like feasible options. So in order to sort of address that, oh yeah, I see now in the plot, yeah, chemical accuracy is marked in the ADAPT-VQE paper on figure 2, and they're all like 5 orders of magnitude below it. Like, what does it even matter at that point what the error is? But anyway, ADAPT-VQE is sort of, I think of it sort of like a neat neuro evolution of augmented topologies inspired thing. I don't know if they are actually neat inspired, but basically you build the circuit as you progress. So it's not like, it's, I guess, structure learning as well as actual parameter learning. The basic algorithm, I'll copy this. This is actually the paper. There's a paper that came out just a few days ago called ADAPT-VQE is insensitive to rough parameter landscapes and barren plateaus. As always, this will be, I'll link these down below. I saw people talking about this online and saying, ADAPT-VQE is, barren plateaus are a big problem for variational algorithms, and people were saying, maybe ADAPT-VQE with these results can solve more variational algorithms or can beyond just these chemistry applications, and that's certainly possible. I tried it out and it's very particular, very sensitive, the algorithm is. So we'll get to that later though. So basically, we have this algorithm, which is, I am putting into the, can I select this somehow? Yes, there we go. Can I shrink this? There we go. Good enough. Okay, so we have the ADAPT-VQE algorithm here. So basically what we do is we go through and we have some operator pool that we define. So some quantum operations. We try each of them, adding each of them to the circuit, whatever. So at the beginning, our circuit is, empty, but later our circuit will be built more. We try adding them to the circuit with some parameter, 0. Sometimes you'll see 1. Sometimes it'll be random. and then you take the gradient with respect to that parameter, and then you add to the circuit the operation that had the largest gradient. And so basically you're trying to estimate, this is a proxy for estimating what's the most important parameter to add, right? Because if you're adding some gate that has a gradient of 0, it doesn't matter if you add it or not, at least at that point in the circuit, because it's not going to change the measurements or the expectation value of the energy. And so that's the basic idea, is sort of as we're going through the circuit for each iteration of this ADAPT algorithm, we're going to want to build our circuit out. Now this has a lot more cost associated with it, because at every iteration you have to re-optimize the circuit. So even if your circuit has, 2/3 the parameters, which could be a big save, you're going to have to optimize it for 1 parameter, 2 parameter, 3 parameter, many times, which is a downside to it. But in terms of the practical benefits, you can often have a lot lower numbers of parameters than other circuit structures. That you'll often see unitary coupled cluster circuit structures, UCC, UCC-SD, stuff like that. We're not going to be comparing to that, because I don't really feel like figuring out how to implement that in Circ or do that, because I don't really know a lot about that side of things. But we're going to just be comparing it to sort of a hardware efficient ansatz. So getting into the actual algorithm itself, it's pretty straightforward. This is why I said this is probably going to be pretty quick. All you won't have to do is just, we already have the basic ideas of, all of this part is already built. We just have to add one for loop here, and then we already have done so much work with VQE before. You can see many videos of it on this channel. So let's actually jump over into the code. Where is my recording? There we go. So if I do that, we can see a suite of standard imports. We're going to be using OpenFermion to generate our molecular Hamiltonians. Here we have a bunch of code that I copied from my noisy VQE video. I'm not joking, I literally did just copy this code exactly. So I'm not going to go through this code in depth. You can check out that video. In fact, you may not even want to check out that one, because I probably copied it from an earlier video. Maybe I should make a sub-series of VQE and QAOA and stuff. But nonetheless, moving on, we have just everything standard here, right? We have our layers, we make multiple layers, we have a VQE that's noiseless, we optimize it to minimize the expectation value of the Hamiltonian. So now we're going to get into the adapt section. And so once again, this discussion of OpenFermion is, if you want to know more about it, go to the noisy video. I guess I'll just link that below. So when we're going through here, what we want to do is we want to say, okay, we're going to be using the expectation layer, because we're going to be messing around with our circuit structures a lot. So using PQC, or the parameterized quantum circuit, is kind of hard, because the circuit structure is, every iteration is changing. So that's going to be a lot of a pain. You'd have to recreate the PQC every single layer or every single iteration, which is kind of inconvenient. And since PQC is actually just a handy wrapper for expectation anyway, we'll just use this. I actually don't know what variable k is supposed to represent here. I don't think it gets used again. I'm not going to delete it though, in case it... Yeah, I don't think it gets used again though. So we have our iteration counter, and then in order to actually implement this, there's some tricks you sort of have to do that we'll get to. But we're keeping track of our parameters and our symbols that our circuit has. We're going to be using Atom as our optimizer. Here we're just doing 18 iterations. You could do more or less. I don't know what the best strategy is. And then we're going to be, so first we say we're going to initialize a random parameter. We're going to add a new symbol, and then we're going to get our circuits from the operators. We're going to specify that this is what we're parametrizing them by is this new symbol. Then we're going to create our trainable variable from these parameters. That will be constant. Both of these, remember, will be constantly expanding as we augment the circuit. And then we're going to go through and get the gradient with respect to this parameter for each of these generated circuits that come from. So these are all of the circuits that we generated from our operator pool. And the way we do that is just by using gradient tapes and calculating the gradients. Note that we should specify, I'm specifying here that we want to watch this variable because the way gradient tape knows how to handle variables, I'm not entirely sure, but when the layer handles it, the gradient tape knows what to take the gradient of. But because this is sort of just an operation, it's handy to tell it, hey, this is what we care about. Watch this variable, basically. So we have our circuit, our symbols, names, our symbol values. We're taking the absolute value of the gradient because we care about the magnitude, not the number, really. And then we want the last one because as this grows, right, this is going to be the gradient with respect to all parameters. And so if we have a bigger circuit, we only really care about the last parameter, which is the most recently added one. So, okay, moving on, we have, now that we have our gradients, right, the one we care about is the maximum, but only if it's actually not tiny, right? If it's the maximum and it's 1 times 10 to the negative 20th, that's just a floating point sort of representation and a meaningless gradient. So we have some cutoff that we're considering. And also, if none of the gradients are larger, then we just put a random choice of insertions. And if it's the first few iterations, I found this is sort of an experiment, right, in stability, because the operator pool, I guess I'll jump down to this now. The operator pool is not the same as ADAPT-VQE. They usually convert basically the excitation, single and double excitation fermionic operators into qubit operators. But, and while that's definitely doable, you have to go through and create fermionic operators and open fermion, then cast them to qubit operators and map those to qubits and circ. That's just a lot of work. And so, and really because everyone knows ADAPT-VQE works on circuits with those, unitary couple clusters sort of ansatz operators. It's not really anything new, but here this is right the circuits that are often used in QML applications, just basic Rx, Ry, Rz, and C0s. And now this is what we're working with. And I'll just make this remark now. I don't think the results will show this, that I found this to be extremely brittle in the fact that sometimes the ADAPT-VQE would converge and a lot of times it wouldn't. Maybe 50-50, honestly, in terms of, that's not true, 70-30 maybe, and converged and didn't converge. So it does seem to be sensitive to the operators. I'm not sure, as far as I've seen, there's no theoretical sort of derivation of or proofs of ADAPT-VQE's convergence. So it's not so much that this violates the assumptions that underlie it, rather it's just not conceptually the same because they're not just different they're not representing the fermionic operators, they're just random gates basically. But this is what it would look like, right, in that discussion of what it would look like for the QML world. So I'll just make that remark. So then we have, if we do have some operators that are large enough gradients, we make our circuit the largest one, or we make our circuit equivalent to the operator, appending the operator with the largest one, because as we go up here, when we generate the circuits, we have our 1 and 2 qubit operators. You could definitely have more or whatever. This is just the way I chose to represent it, the easiest way to do this, basically. So we iterate and we have all of our 1 qubit operators on every qubit and our 2 qubit operators on nearest neighbor pairs. and so then we add that to the base circuit, which is whatever, this constantly expands. And then we go through and we just optimize this circuit. This is the exact same idea as right up here. We just have to specify, we're using the same expectation layer. And then we go through and we cast the params to a list. That way we can append to them. And we just iterate through this process. And here I'm printing out the circuit at each step. If I go back, here's just a random, see if I can add. Here's just an example run right here. You can see as the circuit increases in size and the gates get added, basically. That's all I was going to show there, is that it prints out. So then we go through, and here I just did a couple basically random depths of what the H2 molecule would be. And so H2 is just because it's fast, you can change this to LIH, it would just be slower. And then we plot out the actual results, which I will now show. So here's an example. This is a rare example, actually. I would say around 90% of the time gradient descent converged. So I'm not really sure. I mean, maybe it's because I'm just using adjoint differentiation that sort of alleviates the problem, but that's the barren plateaus didn't seem to be too big of a problem, at least in this case, but maybe that's also just because it's H2. So this is not representative. Do not take this. If you ran it, what would probably happen is that this would be down here and adapt would be up here. Just for the sake of transparency, I'm going to actually run an iteration in the background right now. But you can see there's spikes because this is right after the operator gets added to the circuit, and it has a big gradient on it, so it changed the energy a lot. And so then we're doing descent every time, and in this gradient descent every time. In this case, we are getting close to the target. Here's another example where they both converge. Gradient descent. This is very interesting. I don't know what happened. I mean, it's just found a better parameter, but it's just interesting. And then here's an example. This is probably more like what would happen, is that gradient descent converges very quickly, but the ADAPT-VQE takes much longer. You can see it plateaus, but then it does find a good operator. You'll notice here that I say iterations, and what I'm keeping track of here is that, so this is one run, right? This is one convergence of a VQE. Here's one, here's another one, here's another one. Basically, you have every time you rerun the convergence for every iteration of ADAPT-VQE, I just append it. So this is a comparison of the actual optimization steps required. So even though there's fewer parameters to get there, you have to do more optimization steps. Here's another example where you can see it slowly reaches down to the results. If I share, here's an example I just reran. You can see this is the same as, let me go back over this one, where you have, but this time gradient descent converges perfectly fine. So I have another one running. We'll see if ADAPT-VQE doesn't converge in this case, or if it does. But basically all the point is that for situations in which the operators are not like the fermionic operators, I don't know how well ADAPT-VQE is. And I would encourage you, okay, the 0.8 distance worked fine, by the way, so I'm just going to keep running it. I would encourage you to, I don't know, experiment with this code. You can improve it a lot with the operator handling and generating those operators. But for those of you looking for research ideas, that's a good one right there. How does ADAPT-VQE carry over to non quantum chemistry tasks, maybe QAOA. I don't know what that would look like. Um, maybe you could design the mixer Hamiltonian with ADAPT-VQE or something. But yeah, this right here is the basis of a research project that you could go and do, and a month from now could write a paper on. And I'm being 100% serious when I say that. So um, yeah, that's basically it. That's all I had. I'm just waiting. I could just pause the recording, but I'm just waiting for the uh, run to see if I can show you a non-convergent example. Looks like they're all converging right now, which is not what I was actually looking for. But I should also say that there is a Discord server that I'm a part of that's dedicated to quantum machine learning. So if you are interested in doing this research or any other research or have any questions about software or working with TensorFlow-Quantum or anything else like that, you can always ask the people there. I'll put a link below to join that as well. It's been a while since I talked about that, but it's grown. If I check right now, yeah, there's now more than 150 people in it, which is pretty big, bigger than I thought it would be. So yeah, that's also a great place to ask questions for software and stuff of the people there. Since this is actually taking longer than I thought, I am just going to pause the recording and wait. Seems like they're all working, so we'll just call it here.